Very good morning, class. In the previous video, we have covered some numerical depends on the lever. I've left some numerical, you can try it yourself. The next part of the simple machine is pulley. Pulley is a simple machine which is basically used to lift the loads by changing the direction of effort. If we change the direction of effort, it is quite easy to lift a load. For example, suppose you have to lift a load. Let's suppose you have to lift a bucket from the well, right? So what do? You tie a rope on the bucket and throw it in the well. Now you will push the load like this, right? So you have to, that means the direction of effort is acting opposite to the direction of load, right? Now what if that rope is passing through the pulley? We take the rope, and suppose here we have pulley and the rope is passed through the pulley like this. Like this. Now it is quite easier to lift the load of bucket. Although if the bucket, if the weight of bucket is, let's say, 20 kg, we have to apply the effort of for 20 kg, but by changing the direction of effort, it is quite easy to lift this bucket, because now we can use our human weight, to lift this bucket, right? So it is quite easy to lift the load if we change the direction of effort we are applying on the body, right? So in this case, you can see that load is also here and effort is also here. That means both are acting in the same direction. Just we have changed the line of action of the effort. So that's how we use pulleys. So pulley basically, they are used to, as I said, they are used to lift the load by changing the direction of effort. The pulley can be divided into two parts. First, a fixed pulley. Second, movable pulley, right? As the name said, fixed pulley, the rotation axis of the pulley remains stationary. Like in this example, suppose this is the axis, right? So when the rope goes around the pulley does not move. So this is the example of fixed pulley, and if we tie the pulley like this, and we apply load upwards, you can see that the axis of pulley can be changed. Now that will be known as movable pulley, right? So we'll talk about both of the cases, but first we'll talk about the fixed pulley. So first we are starting the single fixed pulley. Now what is single fixed pulley? A pulley which has its axis of rotation stationary. That means the rotation axis is not moving, it is fixed at a point. It's called a fixed pulley. Okay, this is the definition. Now let's see how this pulley works and what is the mechanical advantage, what is the velocity ratio, and what is the efficiency of this pulley. So here in the diagram we have a single fixed pulley, and we have to calculate the mechanical advantage, velocity ratio, and the efficiency, that is eta, of single fixed pulley. Okay. One concept you must have. There is one concept you must know, that here we are assuming that the mass of pulley is negligible, so that we are not doing any work to rotate the pulley, because obviously you see practically when we lift any load, then along with load there is a motion in the pulley, right? And when there is a motion in the pulley, that means the pulley is rotating, so we are applying some torque on it, that is moment of force, and then the pulley is rotating, that means we are doing some work on it. But if we assume that the pulley is massless, although practically it can't be massless, but we are assuming that we are not doing any work in rotating the pulley because pulley is massless. This is the first assumption. Second, the second assumption we are taking, that there is no friction between the pulley axle. That means when pulley rotates, there will be no friction here, because obviously when there is some friction, so our some energy will be dissipated in the form of friction also, right? So we are assuming two assumptions here. First, the pulley is massless and there is no friction in the pulley, right? Okay. So mechanical advantage, velocity ratio, and efficiency of single fixed pulley. Before you calculate these quantity, you must know the direction, how we show the direction of load here or the effort here. Okay. And one more important thing, that you must know how to show the tension created in the string. So this is load L, right? This is load, and obviously direction of load will be downwards. So this is our single fixed pulley. Okay. This is the direction of load, and obviously because when we are lifting the load, we apply the effort in downward direction. That means here we are applying the effort E. Now there's very important thing here known as tension, because only due to tension this load can be lifted up. Now what will be tension? Tension is basically a reactionary force. It will always act on the opposite to the external force. So here the load is acting downwards, so tension will act here, that is T. And again you can see here the effort is acting downwards, so again here will be tension T. Most important thing, if in a system we have single string, like here you can see that the load and we are applying the effort on the string, they both are common. The string is common. There are no two strings, right? Again, what I'm saying, that load is connected to the common string on which we are applying the effort. If the string is common, then in the whole string the tension will be same. If the value of tension is, let's say, 50 Newton here, then the value of tension in the whole string will be 50 Newton only. That means the value of T will be same here, and that is why I have write the value of tension T, not T1 and T2, because they both are same. Okay. Now when the pulley is stationary, that means in the equilibrium condition, means when pulley is stationary, right? Pulley is not moving. Now, you can see that the load is balanced by the tension T here, because they both are acting on the opposite direction, and the load is not moving anywhere. That means the load is equals to tension here. Equation number 1. Is it clear? Also, we are applying effort here, and effort, you can see that effort is also equals to what? T. Effort is also equals to T. Equation number 2. That means you can see that in single fixed pulley, both the load and effort, they both are equal to the value of tension, that is T, right? So by using equation 1 and 2, what we'll get? We'll get that effort we are applying is equals to load, right? So in single fixed pulley, the value of effort applied on the load is equal to the value of load itself. That means if we are lifting up the load of, let's say, 100 Newton, we have to apply 100 Newton effort to lift that load. Now let's see what is the mechanical advantage, because we know that what is the value of MA? It is load upon effort. So let's calculate. You can take screenshot. Okay, so mechanical advantage is nothing but load upon effort, that is L upon E, and we know that the value of L as well as E is T, that is equals to 1. So mechanical advantage of the single fixed pulley is 1. Okay. Now, the thing is, if the mechanical advantage is 1, that means we are not gaining any mechanical advantage. So why we are using this pulley? So I told you, it is quite easier to lift the load when we are applying the direction of effort in the same direction as the load having, right? If the load, like see, you can see here, it is quite easy to lift a load like this instead of lifting the load like this, right? So by just change, because as I said, we can use our own weight to lift the load, right? Suppose we have, let's say my weight is 70 kg and I have to pull a load of 70 kg. I really don't want to, I really have to apply the load, apply the effort. What if I just hold the rope and hang on it, right? What will happen? The load automatically come up. So this is the advantage of using this pulley. Now let's calculate the velocity ratio of the pulley. Now what is the velocity ratio? Velocity ratio, if you remember, it was in the first part of the chapter. The velocity ratio is basically the ratio of distance traveled by the effort to the distance traveled by the load, right? Now take this example. If the effort is traveled by distance, let's say d, you pull the rope, so the effort is traveled by distance d, then what will be the distance traveled by the load? Obviously the load will also travel the same amount d upwards, right? Obviously, because the string is directly connected, so if 1 centimeter is pulled here, so obviously the other string will go 1 centimeter up. That means the distance traveled by the effort is equals to distance traveled by the load. So what will be velocity ratio? As we said, okay, here we are calculating the velocity ratio, right? So distance traveled by the effort is, this is dE, that will be d, and as I said, it will be equals to distance traveled by load. It is, and the distance traveled by load, that is dl, is also d. They both are equal. What is the formula for velocity ratio? The formula for velocity ratio is distance traveled by effort to the distance traveled by load, right? And we know that they both are equals to d, which is equals to 1. So velocity ratio of the single fixed pulley is also 1. Okay. Now what will be the efficiency? The mechanical advantage is equals to velocity ratio into efficiency, right? So efficiency is mechanical advantage upon VR, that is 1, or simply 100%. It is 100%. So these are the value of mechanical advantage, velocity ratio, and the efficiency of the single fixed pulley. Okay, as I said, that the mechanical advantage equals to velocity ratio equals to 1, and the efficiency is 100%. This is the theoretical case. Practically, the efficiency of the fixed pulley is not 100%. Why? Because when we apply effort on the pulley to lift the load, practically some friction is always there in the pulley. That means we have to apply more effort to pick up the load. That means the value of effort is more than the value of load, right? Practically, the value of effort we are applying on the load is more than the value of load. That means the mechanical advantage will be less than 1. So that is why the mechanical advantage will be less than 1. But the velocity ratio, see, velocity ratio of simple machine does not change. Why? Because obviously when velocity ratio is basically distance upon distance of effort to distance of load, and distance traveled by effort and load doesn't depend upon the friction. If the effort is going down by d distance and load will go up by d distance, there is no relation with the friction. That means the VR, the velocity ratio, will remain equals to 1, and from the formula, which is eta equals to VR upon, MA upon VR. So you can see that the value of MA is less than 1. Let's say it is 0.9. Suppose it is 0.9 and is 1. So efficiency is 0.9 into 100, that is 90%. So you can see that the practical efficiency of the single fixed pulley is never equals to 100%, but it is less than the 100%. In the next video, we'll talk about the single movable pulley. It is very important, and we'll see some numerical on it. Thank you so much, class.